Hi everybody. So I'm going to explain to you the concept of polarization and then ultimately do Malice's law, which you should have derived with the activity. If I've shown you polarization through some demonstrations, then a lot of this will make sense. If you haven't seen it yet, bear with me as you go through this, and then when we meet in class, I'll show you what polarization is and give you some model. Not only show you what the actual Polaroid filter is, but kind of give you some models to help you understand what's going on. It's a fairly abstract idea, but once you get it, it's pretty straightforward. There's not a lot to it. Okay? The reason I'm doing polarization of light in this unit is because polarization is unique to light. It is unique to electromagnetic radiation. And it really is a consequence because light is an oscillating electric and magnetic field. And so that the polarization does not occur with any other type of wave. And that has an important consequence in understanding the nature of light, which we'll get to later on in the unit. Okay, so the first bullet is a recollection of that. What is light? Light is oscillating electric and magnetic field. So if this represents the electric field, and you don't have to draw this, this represents the magnetic field at right angles to that, and the wave goes at the speed of light. C. Okay, so there are many light sources out there. There are light bulbs, there are fluorescent lights, there's the sun, there is light that reflects off surfaces, and most of that is unpolarized. So I'm going to refer to a diagram a little below in the middle of this sheet to help you out. Okay, so let's scroll down and talk about that now. I'm sorry, I have to scroll down up. So let's look at this right here. Okay, so I have a typical light bulb, and what I want us to understand is, let's say that light bulb is a monochromatic source. In other words, there's just one wavelength. Polarization is not about wavelength. Okay, if we have a monochromatic source and it's multiple wavelengths, or one wavelength, excuse me. If it's a polychromatic source, it might be multiple wavelengths, but again, it doesn't matter. Let me start off also saying your eye by itself cannot detect polarization. Okay, polarization is a consequence of passing light through filters, or in some cases the light is automatically polarized, and we'll clarify that. So what I want you to look at are these little arrows there. It looks like snowflake, but what they represent are arrows that are up, down, left, right, and then at angles to them. In other words, all directions. And so what they're talking about in that is the orientation of the electric field. In other words, some of the light coming out of this light bulb, the electric field is oriented, if you will, vertically. Other is oriented, and I guess I'm not drawing it very well, horizontally. And others are oriented somewhere between those two. So we never talked about this to this point because it was never really an issue with waves. But whenever you have waves coming out of the source, how they're oriented, and the simplest extremes are horizontal or vertical, goes to this process of polarization. It would be a lot easier if I could show you the little wave sample that I have in class, but for right now, just accept that, and then we'll make more sense of that when we can actually see something. So anyway, most light is unpolarized. In other words, the plane of vibration of the E field is random. Okay, so if I go back up here, because the vibration of and it's really about the E field, it's really not about the B field, okay, is randomly oriented. Now, what are some light sources are polarized? So what does that mean? That means the plane of vibration is the same. Okay, so maybe it's all vertical or all horizontal or all something between. So plane of vibration is uniform. If you will, either the process by which the light is created preferentially chooses one plane, or we take unpolarized light and we polarize it by passing it through a special filter called a Polaroid. So, common examples, and we'll talk more about later, and this is especially true of modern technology, are LCDs, liquid crystal displays. Those are the displays you see on calculators, laptops, flat screens, smartphones, etc. Not all flat screens are LCDs. Whoops, I don't know why I wrote LDCs. But there is a simple way of telling if they are polarized using Polaroid lenses, and that's something we'll demonstrate in class if we haven't done so already. So LCD stands for liquid crystal display. Another common source of polarized light is laser light. Lasers, by the mechanism by which they're produced, is automatically polarized. So if you could see the orientation, the plane of vibration of the E field, it would be all the same. Again, either horizontal or vertical or some combination thereof. Another way you can polarize light, and this comes from unpolarized light, is when unpolarized light strikes strikes a surface and reflects. So take sunlight. Sunlight is unpolarized. However, in certain cases, when it hits a non-metal surface, especially water, the light that reflects off is polarized. And that light that reflects off is often called glare. So if you're ever standing near a lake, a pond, or even a river, and you see the glare, the reflections, if you will, of the objects on near the bank, like the trees and whatnot, that reflected light is polarized, meaning that all the vibrational orientation are the same. Another way you can polarize light is you can have it pass through what is called an optically active substance. In other words, certain substances, especially sugars and certain crystals, especially crystals in LCDs, will cause unpolarized light to reorient into the same plane and come out polarized. And you can do some interesting things with those. So why does this happen? Well, Polaroid films, which was represented by this or by this, do this because they are made with long chains of molecules that absorb any light that has its E field oriented in the same direction as the molecules. Okay, so that's something it's easier for me to explain in class than right now, but I'll try to just really quickly talk about it. Generally, when we represent a Polaroid material on paper, we represent it as they almost look like slits. Either they're oriented vertically or they can be oriented horizontally. They're not slits. These would represent those long chains of organic molecules usually. And because of this orientation, if a unpolarized light comes in, anything that is vertically vibrating up and down as opposed to horizontally oriented is going to cause the charges in this to basically oscillate and absorb that particular orientation, so that anything that's oriented 90 degrees of this is basically passes through. Okay, so it's a selective filter where the selection is based on the orientation of those long molecules relative to the orientation of the E field vibration. If they match, it gets absorbed, kind of like a resonance. If it doesn't match, it passes through. So that's how you can selectively filter out light. Passing light through a Polaroid filter causes it to become polarized in a particular plane. So this is referring to part B below. In this case, we have a filter that is, just for argument's sake, these are not the molecules. And I know this will get a little bit confusing, but let's say this is oriented vertically. So only vertical light gets through and all the horizontal gets blocked. And so what we have here is 1/2 of the original intensity, because on unpolarized light, on average, half of it is horizontal and the other half is vertical. You might say, well, what about the diagonal stuff? Well, you can break the diagonal into partially horizontal and partially vertical, and in random it'll average out to 1/2 and 1/2. Okay? So vibrations, what I want to say here, to the transmitted light are complete. Okay, so that vibrations perpendicular to the transmitted light are completely blocked. Okay? And those that are in alignment with this orientation. Now again, that's not the molecules. The molecules actually give you the opposite effect, and I'll explain that more. So again, this Polaroid, okay, right here, is oriented vertically, so anything perpendicular to it gets blocked, and only those that are vertical are passed through. Now, we can then put a second Polaroid there called an analyzer and then filter this even further. And that's what Malice's law about, and what your activity was about from the other day is if we orient this at some angle, we can filter out the remaining amount of light. We can go anywhere from letting it all this transmit through to having none of it transmit through. So there's an angle dependence. And that's what the Malice's law is. So basically Malice's law says whatever intensity passes through here, okay, at point C, is equal to whatever comes in, so we'll call that some initial intensity, times the cosine squared of the angle of orientation of the analyzer. Okay, so that angle is measured, generally we'll just tell you what it is, but in this case it's measured relative to the vertical here. So if you put in different angles from anywhere from 0 to 180 and you do some arbitrary intensity, is if we got polarized light now coming in, okay, so again, here it's polarized, here it's unpolarized. Whoops. And we've got to be careful here, because when you take unpolarized light and pass it through a Polaroid, doesn't matter how it's oriented, you're always going to get 50% of your original. What this equation is for is when you have polarized light and then you put another Polaroid material there called an analyzer, then you can reduce it anywhere from 0 or keep the full amount. So if the angle of orientation is the same as the incoming polarized light, in other words, the angle is 0 degrees, we get a full intensity, which I'll call arbitrarily 1. Then you learn that if I make it at 90 degrees to that, in other words, perpendicular, you will attenuate the light completely. The intensity will go to 0. And then if we go back to 180, which is right about here, we will be back to full intensity, because if this is 0, I flip it all the way around to 180, well, it's still vertically oriented. So if I fill in the gaps here, okay, and if I do like the cosine squared, if I put in 45 degrees, I believe the cosine squared of 45, cosine of 45 is radical 2 over 2, so squared would be 1/2. We are going to have 1/2 the intensity at 45. So we're going to get something like this as our graph, and that's hopefully what you saw with your activity. And then we could continue this on all the way to 360. It will just repeat itself, but I'm just generally restrict ourselves from 0 to 180. Okay, so in a few minutes I have left, let's do a quick little example. So on a diagram on the front page, so that was the A and B. After light passes of intensity I0 passes through the polarizer, what is the intensity? So if we go back to this diagram, here is the I0. Here is the polarizer. How much light do we have here? I've already answered that. That's automatically going to be 1/2 the original intensity, no matter what the orientation of this is. Okay, so let me go there. So that's going to be 1/2 the original intensity. Now, this passes through the analyzer, and the analyzer is oriented at 30 degrees. So we want to know what the new intensity is. So I'll call that I prime. So I prime is going to be equal to the intensity coming in, which is 1/2 the original intensity, right? That's this value right there, times cosine squared of 30. Okay, I think cosine of 30 is radical 3 over 2, so squared is 3/4. So I have 3/4, that whole thing is 3/4. So 3/4 of 1/2 is 3/8. So we're going to get 3/8 of the original intensity. Okay, so the original intensity, 3/8 of this original intensity. And I know that can be kind of I'm sorry, that's the original intensity that came in right here, my bad. So we have 1/2 here, and then we lose another 3/4 of it. I will do example 3 in class, okay? In fact, why don't you try sample 3? Maybe you'll get it, maybe you won't. This part is easy, this part is a little bit more difficult, but basically to do this one, you just have to apply this equation, the I squared, or I0 cosine squared, twice. Okay, so good luck with that, and then we'll pick up from there and do demonstrations.